Hello, welcome to the Scottish Civil Society Data Partnership Project webinar series. This is the 6th webinar of a group on the theme of research on civil society in Scotland and connections between academic and other research organisations. Are we brought?
Yeah, I'm not hearing you.
We're not sure if the volume's working smoothly. Is this recording clearly, Alasdair? We might just pause for a sec if.
Okay.
Here I am again. This is broadcasting fine, we believe. Okay, so take 2. Welcome to webinar 6 of the Civil Society Data Partnership Project webinar series. This series in general is about research on Scotland's civil society and connections between academic researchers and researchers or data holders in civil society organisations. Our webinars are going through a number of different topics about aspects of research with data about civil society. Today's webinar has an interesting series of presentations on visualizations, one of the most variable and exciting ways in which data can be summarized is often through graphical visualizations or visualizations of different formats. And we've got a series of pre-recorded talks this afternoon on features of visualization of data resources. Our first talk is a general introduction to some themes in visualization, and then we've got 3 more specific presentations where we're exploring particular topics about visualization, software tools, geographical data, the understanding of uncertainty, for example. So what we'll do, as in previous webinars, is we'll run through a series of the videos. We'll pause briefly between them. We have the facility in the webinar series to pick up on comments or questions that people who are watching this live might post during the course of the presentation. So we'll be looking out for them, and we may pause and discuss those if any come up. Otherwise, we'll just move through each of the 4 presentations. So let's begin with the first presentation, which is by Alasdair Rutherford from the University of Stirling, part of the Civil Society Data Partnership Project. Presentation's about 20 minutes, and it's on the theme of graphs and charts, the art of data visualization.
My name's Alasdair Rutherford. I'm a senior lecturer in social statistics in the School of Social Sciences. And I'm going to talk about data visualization, producing graphs and charts to show your data. You'll be learning about different measures, different ways of describing data, different ways of looking at associations. And I want to talk about how you might present those and visualize those for a number of different purposes. And this really combines some statistical understanding of how you collect data, how you analyze data, how you interpret data, along with some principles of design and communication about how you explain the story that comes from your data, how you talk about the findings. So I'm going to talk about what data visualization is and why we need it. We're going to look at some common graphs and charts, some common ways of presenting data, some of which will be familiar to you already or that you'll have seen around. I'm going to talk a little bit about some of the developments in data visualization, some of the newer forms of visualization, look at how you choose the right visualization, what are some of the issues you need to think about in presenting your data visually, and then lastly finish up with some examples of the dark side, how visualization can mislead. So when we're presenting data, it's not just about pretty pictures or about replacing a table with a chart and introducing some color. It's about thinking a bit about how best to present complex data, the relationships that make up the findings and the conclusions that you're drawing from the data. And there's a number of different reasons that you might do this. So you might be wanting to summarize your data in the same way that you'll do some basic descriptive statistics to look at the average and measures of spread. When you're starting your analysis, you might want to take a look at the data and see what the distribution looks like. You might use visualization to start doing your analysis, to actually identify potential patterns. What sort of relationships between variables does it look like there are, that you might then want to use some of your statistical tests to investigate. Once you've done your analysis, you're going to need to present your data. So you might use visualizations as a way to communicate the analysis that you've done and the findings that come from it. And then if you're building that into making a case, into demonstrating an argument, into presenting some findings, you might use the visualizations as part of telling a story of the findings of your data. Although there's been lots of recent developments in data visualization, it actually has a long history. One of the pioneers was Florence Nightingale. If you're interested in finding out more about that, there's a link to a short video on YouTube on the slides, which you can look at later. But Florence Nightingale used data visualization in the Crimean War. There was lots of statistical tables about the deaths of soldiers. That was obviously important, had an impact on large numbers of people. And she used some clever visualization to show that the death rate was far higher among soldiers that were in hospital and from preventable diseases and injuries rather than on the battlefield, and used this to make a case for better hygiene and cleanliness standards in hospitals. So that was going to have a bigger impact on people surviving. And to show the size of these effects, she used graphs and visualization rather than just presenting statistical tables in order to tell that story and to make that case. So there's lots of different visualizations you can use. I'm going to talk briefly about some of the more commonly used ones: bar charts, line graphs, pie charts, scatter plots, that are pretty typical, and you're likely to start producing yourself. And there are different ways to produce these sorts of graphs. Many of them can be produced in spreadsheet software such as Microsoft Excel, the statistical software, and then there are increasingly online tools that you can use to present data in interesting ways. So first of all, bar charts then. Bar charts are particularly useful for presenting categorical data. So data that is which category people are in. They present the categories along the x-axis, the horizontal axis, the bottom of the graph, and then the height of the bars usually tells us the averages, percentages, frequencies on the y-axis or the vertical axis. And one of the big advantages of a bar chart is that it shows you proportional as well as absolute differences. So you can see that some amount is twice as much as another because the bar is twice as big. So you don't just get a sense of the absolute value, but you get a sense of the relative values as well. So this is a graph of Twitter activity by day of the week. So we've got categories here, Monday to Sunday, and we've got the percentage of tweets on that day. And it gives you some sense of this pattern. There's not a lot of variation, but there's the highest number of tweets on a Tuesday and Wednesday, and it's the lowest on a Sunday. Okay, so we get some sense of spread across the week, rather than just presenting it in a table. Categories are on the x-axis, the percentage of the activities on the y-axis, and that communicates the spread. Okay, we might also have more continuous data, particularly if it can be grouped on the x-axis. So, for example, years of age. Age is a continuous variable, but if we think about it as age in years, we can treat it as categories. We can look at the percentage of Twitter users in each age. So we've got age categories here. There's an ordering to them, and the height of the bars show the percentage, so that we can see that the bulk of Twitter users are sort of 20 to 25, but there is a long tail here of older users of Twitter as well. So we get some sense of both the kind of middle of this distribution and also the spread of the distribution, how variable it is, how likely it is to see different values. So we'll quite quickly communicate that spread of our data. And in this bar chart, the categories here are ordered. You're getting older as you're going to the right. Line graphs are mostly used to present continuous data or metric data, where we have a variable that's not in categories, but it's a continuous quantity. Although they can be used for ordered categorical data, but that makes the most sense when it's approximating an underlying continuous variable. And it's best when you want to show changes across the values of the x variable. There is lots of data that you could choose between a bar chart or a line graph. The line graph is best when there's some ordering to those values, and maybe perhaps some sense of change across those values that you want to capture. So this shows the average number of tweets per day by how many followers the users on Twitter have. And so we've got some types of movement. As the number of followers increases, how does the frequency of tweeting change? So we can see for people up to about 800, 900 followers, it's pretty flat at around 3 tweets a day. There's not a lot of variation. When people get above 1,000 followers, these are the accounts that are tweeting much more frequently, and then it climbs after that. So we get a sense of this shape and this change across the number of followers. Okay? They give us some sense of a trend across that data. Pie charts then are a common and accessible way to represent percentages and proportions. So rather than absolute values, what percentage of the sample do the different values make up? They need to be used with categorical data because you need each slice of your pie to be a category. The categories don't have to be ordered, but they do have to be mutually exclusive. So everybody has to be in one category or another. The pie chart isn't going to work if people can be in more than one category. So your percentages have to add up to 100%. So this is the data users by age group. You can see from the key, the colors that apply to the ages. And this is the percentage. So the percentages add up to 100 and make up the whole pie. Okay, so the area of the segment represents that percentage. And when the data is ordered, it can be easier to see combinations. So for example, the blue and the red here is telling us the percentage that are between 15 and 24. We can sort of add them up. We can see that that's about 2/3. So when there is an ordering to the categories, that can be helpful in reading sort of groups of categories from the pie chart. It's not going to work so well when you want to compare, the size of this slice to a slice that's not next to it. If they're not, it can be difficult to judge that area, and that's one of the drawbacks of a pie chart. Our fourth graph type then is the scatter plot. Scatter plots allow you to compare the values of two variables, and specifically metric variables, so that are interval or ratio, that are continuous data. And so rather than just describing one variable, they're useful when we want to look at potential relationships between those variables, and to look at those patterns, which we might then go on to test with some of our statistical and inferential tests. And they're also useful for spotting outliers, cases that don't fit the pattern, that are quite different, and that we might then want to understand why those cases are different. So here's an example of scatter plot of spouse age. So this is the age of the wife. This is the age of the husband. This is data from the British Household Panel Study from 2008. And so each dot here is a couple, and you can read off the age of the wife and the age of the husband from the position of the dot. Okay, so first of all, it gives us a good sense of a trend here that ages tend to be fairly similar in married couples. People that are older tend to have an older spouse, but also that there's quite a bit of variation around that as well. So we can see some outliers, for example, a particularly old husband and a particularly young wife. There are a number of couples that are away from this trend. So here we can see quite a strong relationship with this. As we would expect, there's quite a strong correlation, but also get some sense of the variation around that association, and look at outliers as well, which might be genuine outliers or might also be coding or data entry issues. And then lastly, combining some of these ideas are our box plots that give us quite a lot of information about our data. So it shows you the proportion in different quartiles, splitting the data up into 4, and also gives us different measures of the middle of the data and lets us compare distributions. So we'll typically have a box plot like this. The shaded box here is the 25th to the 75th percentile, so a quarter of the data is below here, a quarter of the data is above here. So of course, this is half the data in here. So that gives you a sense of where the middle half of the data is. It shows you where the central value is, the median, and also where the average, the mean is as well. And then these whiskers give you some sense of the more extreme values of the data. And then individuals that are right outside that range are often marked as outliers as well. So this gives you a sense of the spread, because the bigger this central box here, the more spread out the middle of the data is. The further out these whiskers are, the further away the outliers are, the edges of the data are, and then it also highlights particular outliers. So it's got a lot of information in the one graph that can help you understand the center, range, and spread of the data. You can then combine those into a more complicated graph where you're comparing values across different categories. Okay, so you're able to see that for different countries, not just the averages are different, but the spreads are different, the ranges are different, and so you can use this in order to start looking at relationships, combining categorical and metric variables. So those are some of the traditional graphs that you'll see most commonly and that are generated by packages such as SPSS. With improvements in technology and more input from graphic design, as well as increasingly available data, allowing people to do more with open data, with data sources that become available. There have been a range of developments in data visualization and attempts to make data more accessible and the communication of findings from data more accessible. So we can look at some alternative variations. So this is an area plot. So it's carbon dioxide emissions. It shows you the carbon dioxide that was released up until the year 2000. The carbon dioxide added since 2000. How much more we could safely release without affecting the climate. The size of the fossil fuel reserves, and then the estimated remaining fossil fuel reserves that are undiscovered. And so you get a sense of the relative sizes here compared to the carbon budget is described what's left to release compared to the amount of carbon that's left in the ground. So this, by using area and color, is able to communicate the relative sizes of these numbers more persuasively than just a table might. So it provides an alternative to the bar chart where we're using height, we're using area. The advantage of area is it's quite easy to compare them. It's quite easy for our eyes to tell whether one area is bigger than another and make comparisons. And this visualization also includes the numerical data, so you can actually read off the numbers as well as getting a sense of their magnitude. Other graphics are incorporated to make some of the visualizations easier to understand. So this is looking at typical Twitter users. If the Twitter community were 100 people, so you could think about each person here as being like 1% of the Twitter population, because there are 100 people here, and then the color is used in groups to show the characteristics of that population. So we have 20% are dead, are empty accounts that aren't active. 50% here are lazy, they haven't tweeted in the last week. Only 5 have more than 100 followers. There are 5 loudmouths creating 75% of the tweets. So there's 5% of the Twitter users are creating 75% of the tweets on the site. And then you can get some sense of the gender balance as well, perhaps. So this is kind of an alternative to a pie chart because it's giving us a proportion, but we can easily read off the percentages. And it's containing a range of information by the different combinations of the groups, and in quite an attractive and accessible way. So that's lots of different visualizations that we could think about. And so the question is, how do you choose what visualization to use? How do you know when to use a bar chart or a line graph or a pie chart or to do something more complex? And the 3 questions that I would suggest are important in making that decision are, firstly, what sort of data are you using? So some of the examples required categorical data or required metric or continuous data. Some of the visualizations are a combination of the two. So the type of data that you have is going to make some of that decision for you as to which visualization is appropriate. And that's true when you're choosing the statistical tests and the methods that you're going to use to work with your data. So it's really important to know what type of data you're working with. So that's going to be the first thing. Secondly, you want to think about what characteristics of the data do you want to communicate? Are you trying to communicate the absolute value of something, the total amount of carbon, or the number of people using Twitter? Or are you trying to communicate something relative? What percentage of Twitter users are female? How does the amount of carbon we've emitted compare to the amount that's left in the ground? And you're wanting to make a comparison between quantities, or a relative message rather than absolute. Are you trying to communicate just the middle of a distribution? Do you just wanting to show the average, and so a bar chart just show an average? Or are you trying to show the shape of the distribution, so some sense of how similar or how different members of that sample are? So you need to think about what it is that you're trying to communicate. Use all sorts of different graphs, but what is it that you're trying to say with it? And then lastly, who is the audience? Because you want to produce a visualization that is understandable to the audience that you're trying to communicate with. So for a research audience, for an academic audience, then the box plot has a lot of information about the distribution, and you can read off really efficiently lots of characteristics of subgroups within a sample. But it is a little bit difficult to read if you're not familiar with a graph like that, and so it doesn't necessarily convey that information straight away to people who aren't used to reading graphs like that. So some of the visualizations we looked at the end can be more accessible, particularly in use of color and shape and area, that you can look at it and pretty quickly get the essence of what it's trying to say. So you need to think about who you're trying to communicate with, to ensure that the graph, the chart, the visualization that you use is able to convey the message you want to the people that are consuming it. So just like the numbers themselves, data visualization can be used to mislead, and this might be accidentally because you don't label the axes right, or you don't produce the right chart for the data that you have. Or there are also examples of data visualization being used to intentionally mislead in the same way as there can be with numerical statistics. You need to be particularly careful when you're using percentages, that you're clear when you report a percentage, what it is a percentage of. Is it a percentage of your whole sample? Is it a percentage of a particular category? Is it a percentage of people with particular combinations? Are the categories exclusive, so the percentages all add up to 100%, or can people be in more than one category, and so that doesn't make sense? And you also particularly need to pay attention to the scales in your graph. So the eye is perceiving shape, area, color, and by changing the scale of your data, you can change how relative sizes look. And so you have to make sure that you're picking an appropriate scale that is honestly communicating the underlying data and isn't being used to hide or conceal some characteristic of the data. So to sum up then, there's lots of different data visualizations available to use, from our sort of traditional bar charts and line graphs and pie charts to some of the more innovative area plots and data visualizations, and even dynamic visualizations that are interactive, that let you change things and see how the data moves if it's online. It's important to choose the right graph or chart in order to describe your data. So it's a really good way to get a sense of to get a feel for your data. So you're still going to want to produce the sort of summary statistics of the measures of the center, your averages, your measures of spread, and so on. But it's also a good idea to have a visual inspection of your data, to have a look at that distribution and get a sense of whether it's what you expect. Are there observations, are there outliers, are there values that don't make sense that you want to investigate further? Sometimes doing that visually can be more intuitive. You do need to choose the right graph or chart when you come to the presentation of your findings, or the telling of the story, or the writing up. There'll be lots of possible charts you could produce, and you need to think about which one tells your story, demonstrates your findings, and what type of chart is appropriate for the data that you have and the audience that you're trying to communicate. And lastly, you really need to be aware of misleading with your visualizations, either intentionally or accidentally, particularly in your choices of scale, in terms of percentages, because there are a number of traps that you can fall into. But thinking about some of these principles and about how your audience is going to read and interpret the graphs and the visualizations you produce can make the analysis and the presentation of your findings from analyzing data much more accessible, much more persuasive, and reach a wider audience to communicate what it is you've done and the findings that you have from the data that you've analyzed.
Great. So Alasdair was talking there about data visualization, what we mean by data visualization, some of the techniques of analysis or techniques of presentation that are used to present statistical data, and also some of the challenges and pitfalls of using graphs and various images to present. We lost vision briefly within that presentation, but we think we know what the problem was, and we think we'll be able to avoid the same thing happening again, hopefully, when we show the recordings. So the next 3 recordings that we've got lined up are about slightly more specific aspects of the process of producing visualizations. Later on, we'll have talks by Orian Brook on geographical data visualization, and then again by Alasdair Rutherford on the idea of visualizing uncertainty. The next talk, though, that we'll move to is by myself, which lasts for about half an hour, on software tools of visualization. I should say for this talk and for all of the ones that we're broadcasting, there's materials you can download from the thinkdata.org.uk website, including supplementary example files in the case of this software talk. So we'll move then to a recording by myself on making graphs with academic software tools. Hello, this is Paul Lambert from the University of Stirling, and I'm talking about how we can achieve the visualization of the results of statistical data analysis through 3 popular statistical analysis software tools that are widely used by academic researchers. I'm going to talk about SPSS, Stata and R, 3 packages that we've also introduced in other webinars and workshops associated with the Scottish Civil Society Data Partnership Project. Now, for this webinar, there are also some downloadable materials on the thinkdata.org.uk website that might be helpful. There are some examples of command files or syntax files in the 3 different languages that you can download, and that include illustrations of the things I'll talk about. You might also want to pick up the underlying slides on which I'm basing this presentation itself on, to follow in more detail at a later stage. So, making graphs with academic software tools, and by these tools I mean statistical data analysis tools. Now, not everything in the world that you might produce as a visualization can be achieved through a statistical analysis software tool, but a great deal can. Sometimes some of the visualizations you might see on things like news media will be based on specialist software for graphical production and so forth. But really, a very large volume of statistical analytical summaries can be achieved through graphical formats in widely used statistical analysis software packages, the packages we'll talk about today, for example. One category of those visualizations in this webinar I'm going to describe as the classical or routinized tools of graphical summary. Ways of displaying statistical data that have been around often for more than a century, that are widely understood and widely used. Things like bar charts, line plots, scatter plots, for example. I'm highlighting Darrell Hough, How to Life with Statistics, which was written in the 1950s, an influential statement on using social statistics, full of comments on
graphical representations of statistical data, for example. The software tools I'll talk about today, SPSS, Stata and R, a convenient feature of them is that they integrate facility for graphical display along with facility for doing other things with your data set. So undertaking statistical analysis through modeling or descriptive statistics in combination with graphs, which makes them particularly convenient for use for research purposes. And one comment about using graphs that it's useful to think of is that we're not always talking about producing graphs for the purposes of publication or dissemination. Certainly that's one way that we do frequently use graphical presentational data, both in academic and in other sectors. But actually a lot of the construction and use of graphs is often just used by the researcher themselves as part of the process of better understanding their data. So for example, when I work personally through analyzing data, I'm always producing lots of different graphs, which are just there to help me understand what's going on in the data. They don't necessarily go any further than be produced for the analysis process. So a large volume of graphs are available that in a certain sense are classical routinized things that we've known about for a long time. At the same time, the current era is open to many innovations and ongoing developments in graphical representations of statistical data as well. And I'm going to try and mention a few of these when talking about the specific software results. So these innovations arise for various reasons, including technical developments of the capacity of software. We see innovations in the way that we can present graphical results, fancy graphics doing different things than we thought of before, non-classical, essentially new things. Also, many of the graphical innovations in presenting statistical data actually arise from developments in the analysis of statistical data rather than in their display. So new ways of approaching the statistical analysis generate new forms of summary statistic, different priorities in visualization. If you've heard of Bayesian statistics or Bayesianism, that's a style of statistical analysis which puts an emphasis on the multiple plausible patterns that are associated with a data structure or data result. And that leads in turn to interest in visualizing uncertainty about statistical values as much as their specific calculated results. And that leads in turn to innovations in graphs that communicate that uncertainty in some way. Also, another reason we're seeing innovations in graphs is because it's becoming easier to share graphs or to use graphical representations of data in a more innovative way. So, for example, online publication outlets, the possibility of placing appendices online with research reports and so forth, often prompt people to produce and disseminate a wider range of more ambitious graphical representations than they might have done in the past. So we've got an idea of classical or traditional graphical tools and innovative graphical tools. One last comment to make about using statistical analysis software when producing graphs is the convenient possibility of clear documentation of that process through usually the command language of the relevant package. For those of you that have watched some other webinars presented by our group or been to our workshops, you'll know that we always stress the value of any sort of research featuring documentation for replication. That is sufficiently clear documentation that you could easily redo it yourself or pass it on to somebody else that they could redo it in a convenient and a quick manner. This is when we're talking about analyzing statistical databases, this is usually achieved by using command scripts or syntax, writing out code in the language of the relevant package, and that code serves as the documentation or record of what you're doing. Now, this possibility is very much there for producing graphs to represent patterns in statistical data. Just like other sorts of analysis activity, the production of graphs through software can be documented through command scripts or syntax. And actually, the downloadable files on the thinkdata.org.uk page are 3 examples of command scripts in the 3 different languages. I've called them CSDP Webinar 6 and then SPSS Do and R, respectively, for SPSS, Stata and R format command files. So on the screen, I've got an illustration of some code in Stata that produces a graph. And after talking in general terms about the 3 different packages, I'll try and briefly illustrate applying some of that code in each of the packages at the end of this webinar. But the initial point is that a very convenient feature of the existing statistical analysis packages that are widely used by academics is they have this capacity for recording the production of graphs through a command language format. So let's talk specifically about each of the 3 packages, SPSS, Stata and R. And we'll start with Stata, which is one of the most popular tools for survey research at the current time, and does feature very positively a combination of a very wide range of statistical analytical capabilities and also graphical capabilities. I've put a do file online, a syntax file in the language of Stata that you can download and that features a number of examples of commands. It has some onward references to websites where you can find out more examples. Mitchell 2012 is a textbook on producing graphs through Stata. The classical or routinized graphs in Stata, to my understanding, Stata has pretty much all the regular options available, the scatter plots and bar charts and line plots and so forth. Stata, like all of the packages, also, you can think of it as working almost in a 2-stage process in producing graphs. When you ask for a graph initially, it'll come in a series of default formats, whatever the standard display setting is in Stata. So on the top of on the right of the screen, we've got the default layout for a bar chart showing the average of a variable. It's IMPAVO, which is a measure of volunteering from the European Social Survey, a data set that spread across all the countries, a number of the countries of Europe. So the average volunteering by country. The image towards the top is the default in Stata. The image towards the bottom is the same data, but after I've made some minor adjustments to its formatting and layout to try and get to a better presentational form. I've lengthened it, but narrowed it, and I've changed the color, for example. And I've also brought in another image in the same group, which is from a slightly different analysis of the same phenomena. All of these using conventional, routinized graphical approaches, but with minor adaptations to formatting and display. So we've got the classical routinized approaches. Stata, like all the software, also features various innovative developments in graphical plots or emerging things that are increasingly used to communicate data. There's lots of different things that you could discuss in terms of what Stata can do. I've picked on 3 examples that I see a lot of in my own field, but you may have different views on what's innovative or exciting. We increasingly see people using this sort of graphical display shown on the top left of the screen, which is usually referred to as a trellis plot. What it shows is a series of mini graphs split up by different categories that are important to the data. Actually, this trellis plot has got pretty much the same data as is in the messy line plot on the right of the screen. It's the relationship between education and volunteering from country to country. But arguably, the trellis format display makes it easier to see the differences in the patterns from country to country. It makes it easier to make comparisons and see things more neatly than a graph where everything is overlaid. 2 more things that could be thought of as innovative about the capability for graphing in Stata, shown in the 2 images on the lower left of the screen. The bar chart is a summary of summary statistics. What I've done is calculate correlations between education and volunteering for men and women separately and for different countries separately, and then I've set those all up into a bar chart. This isn't rocket science. It's not a especially complex thing to do, but what's very convenient and attractive about Stata specifically is it's very easy to do this sort of combined summary graph all within the package format. other ways of working. People might produce the correlations, say in Stata or SPSS, and then transcribe them into Excel and make a graph in Excel of a similar look. Stata conveniently allows us to do all of the different stages in the same environment. And bottom left of the screen, adjusted predictions. These are predicted values from a model predicting the probability that a person volunteers, again using the European Social Survey data set for 3 countries. This graph is summarizing something known as marginal effects, which are special statements about probabilities taking account of other values or other characteristics of people involved in the data. I mention this because the graphical summary of the results from statistical models, which is what's captured in this image, the adjusted predictions, is, to my view, another emerging area of graphical presentation, where Stata in particular has some very convenient facilities for summarizing the results of models. So Stata has a mix of more traditional graphs and more creative or innovative ways of summarizing data patterns available. The same is true of SPSS, and it's also true of R. I'll make some comments on these 2 software and then try and have a moment looking at each of these packages in turn. Likewise, in SPSS, I've put a downloadable syntax file up on the thinkdata.org.uk website, where you can pick up examples of producing these graphs in SPSS. Typical examples of traditional or classical or routinized graphs. I'm illustrating this with bar charts, but SPSS, like Stata, has all the usual suspects. It allows you to produce scatter plots, line plots, etc. All the things that we're used to as commonly used graphical presentations. Like Stata, SPSS has a sort of a default output format, and then the user has the possibility of tinkering with that and trying to improve it. So I'm showing on the right here the default format for a bar chart, looking at the average levels, the proportion actually of people who volunteer across Europe, actually, for men and women in different age groups. I've manually edited it within the SPSS environment to get what arguably is a slightly nicer display. I've increased the size of some of the notes. I've changed the shading so that it would print better or it's easier to distinguish. In the case of SPSS, these manual edits were actually achieved by pointing and clicking and typing on the output interface in a manual way, rather than being able to achieve them syntactically. This is a difference between SPSS and the other packages. Comparable levels of precise manual coding in Stata and R would be achieved through syntactical commands, but in SPSS, there's an element to which some of the edits need to be undertaken manually, interactively, which I would argue isn't such a positive thing, but it can be convenient in some situations. So as well as the more routinized types of graphical approach, SPSS also features a number of innovative tools of analysis as well in different formats. I've illustrated a few of them in the downloadable syntax file. What's on the screen is, for example, a graphical summary of the results of a statistical model. More usually, software packages, when we undertake statistical models, produce tables of coefficients that tell us about the average influence of different factors on an outcome, for example. SPSS has a new innovation where it's representing the same data through a variety of standardized graphical forms. So this is a way of presenting the importance and the direction of different parameters as influences on an outcome in a regression model. Whether the coefficient is positive or negative, represented by color, how relatively important the factor is on the outcome, represented by thickness of line. An interesting development. It perhaps has different attractions and limitations depending on your preferences for graphical presentation, but it's certainly an innovative development associated, in this case, with the package SPSS. So what SPSS and Stata are quite widely used by social science researchers for data analysis and also for producing graphs. There's a third package which is rather different in a number of ways, but is also available for both data analysis and graphical production. R, which is a freeware, has a tremendously wide range of data analysis functionalities and graphical presentations, but as we've introduced it also in previous webinars and workshops, it's also a rather challenging software to work with. It requires a level of programming that's considerably more advanced than some of the other software that are typically used in the social sciences. I've put some examples of R code in the downloadable script file and some onward references to other sources of information about producing graphs in R. R does have a long-standing tradition of capacity for quite high quality graphs, including in its standardized, routinized graphical formats. I've shown on screen how some of the routinized graphs in R typically look: box plots, scatter plots, line plots, and a mixture of line plot and a scatter plot here for the best fitting line for the relationship between age and volunteering and the underlying data. Lots of nice things that you can potentially do with R, but I would warn you that it's a bit more work in producing good quality graphical outputs through the R language than maybe in some other formats. One area where R is pretty strong as an analytical tool and visualization possibility is that a lot of ongoing statistical development is undertaken in the language of R. A lot of professional statisticians working with R, for example. And so new techniques of graphical summary that are associated with analytical methods often first become available in R before they become available in other packages. On the left of the screen, I'm showing an example of that, which is associated in particular with the Bayesian approach to analysis and has been recommended by a number of people over the last decade or so. A way of summarizing a regression line, in this case, the relationship between education and volunteering, but by also recognizing the uncertainty about our estimates of the line. The main line as comes out of the model is the line in the graph that's in red or pink. Around that, we've also drawn some other lines. And the point here is that these other lines are also plausible alternative lines. The point estimates have margins of error around them, which means they could be a bit higher or a bit lower. So all of these other lines are actually also plausible within the margins of error. And this style of graph I've produced by using an extension library in R, which produces simulations, random simulations from the range of plausible values, and the QQ plot extension, which, the GG plot extension, which gives us extra control over the graphical display, leading to an end product which is quite nice and sophisticated as an expression of statistical patterns in the data. So I've been talking about using software to summarize patterns in data. I've mentioned that there's a lot of different graphs available in all the packages and that it's particularly nice to be able to do most of them through a syntax-based format. And I've also stressed that not everything in the world to do with visualization can be achieved through these data analysis packages, but quite a lot can. Let's have just a quick look at implementing some of those graphs in the languages of some of these packages. First of all, I'm going to Stata. On screen, I've got the CSDP Webinar 6 data file. It's going to use the European Social Survey data, which can be downloaded from europeansocialsurvey.org. So if you're wanting to follow any of the example files, you'll need to go along to the europeansocialsurvey.org website, download the data in SPSS or Stata format, from which it can be read in SPSS Stata and also R as well. When you download this, you get a large data set with typically about 40,000 records from samples of 1,000 or so from different countries in Europe. These examples, I'm using the round 1 European Social Survey data extract. So I've downloaded that onto my machine. It's stored at this location on my machine, and I open it in Stata with a command that basically says use these variables from this file, which is located in the h:/data subfile, and in the actual file name ess1e01.eta. So for example, in Stata, if I open up the ESS data and ask for a distribution of one of the variables within the data in Parvo, this is the output from those lines. We've got a variable with 10 categories of importance of voluntary, how important people think it is to be involved in a voluntary organization, where 10 is the most important, and we've got some missing categories. Now I'm just going to run over some preparatory stuff on the data that's not too important. I'll just run that over in the background. But then some examples of using syntax code to produce graphs in Stata. I've written a number of different illustrations in the Webinar 6 do file. Feel free to download and look at it in your own time. Graph two-way is a common way of producing graphical outputs in Stata. QFit will fit the best fitting quadratic curve to the relationship between the variables in Parvo and age. Run that little bit of command, and I get this image, which is age by importance of volunteering, and we see the best fitting quadratic line has this N-shaped curve. In general, older people think volunteering is more important, but when you get amongst the oldest people, that relationship seems to turn around on average. Now, a takeaway point about Stata is that we have the baseline models, but then we have variations on them that we can make by small edits to options associated with them. So this next bit of code does exactly the same analysis, but I make a number of manual changes to the display of the graph by looking up what available options there are for this command and implementing them as I prefer. This leads to this slightly different looking graph. I've given it a title, a footnote, subtitle. I've changed the color and thickness of the line. I've changed the size of the graph as well. I've made it more elongated. These are all matters of preferences, but the point here that I'm trying to make is that with a bit of editing, you can typically get to quite decent quality graphical displays in Stata. The default graphs you might not want to think about publishing in your final report, but with a little bit of editing, you could come up with something that looks quite nice in different ways. So that's producing graphs in Stata. Number of points made that are hopefully self-explanatory for those of you interested in the syntax file that's downloadable from thinkdata.org.uk. Let's have a look at SPSS. Doing the same thing with the same data. I'm opening up the European Social Survey Wave 1 data file, keeping a subset of variables that includes some data about volunteering, and running some data preparatory work on them. If I send that to run in SPSS, I'm opening up the data file, running the distribution, making some changes to the data. Some results are whizzing by. Got a number of different measures that I'm going to work with. Here's the default histogram in SPSS. Typical classical or routinized type of graph. Here's a default measure of format of a bar chart. This is actually the same one that I had on the slide earlier. The default display is okay, but we might want to make minor edits to it. And you can see as I'm hovering over it, double click to activate. In SPSS, these minor edits would be achieved manually. So if I open up what's called the chart editor in SPSS, I can then start clicking on the chart and changing things. So I've clicked to highlight the blue bars, the bars for males. I'm going to change, maybe I can change their color to a lighter shading. Maybe I can change the formatting of the labels. Change them to bold. Change them to a different angle, 60 degrees. Did that work? Not necessarily better, but just trying to illustrate how bit by bit we can make edits to the graph, arguably come up with something that's a little bit nicer to look at. So SPSS is a bit more intermediate when on this theme of documentation for replication. We can produce the classical graphs in SPSS quite nicely, and there are some more innovative and interesting graphs available too, of examples in the syntax file. But typically there is an element of manual editing as well to tidy things up or to make things look a little bit nicer. Last example, R. R is a little bit more complex. If you open up the R code, downloadable from thinkdata.org, you'll see things are just a little bit more confusing. The code is less intuitive and there's more of it. Yeah. Sorry, I made a little mistake there. I'm going to be working with a subset of data called ESS extract in terms of R. These are the column headings for ESS extract, but that's the subset of data from the European Social Survey. That's what I'm going to work with in the main analysis. ESS extract is known as an object, and within ESS extract there are the different variables. EDU years is one of them. It's years of education. If we want to do something with something from an object, in long format, we would give both the object and the variable. So ESS extract $edu years means focus on that column within that data frame. Table is essentially a frequency distribution. And this is years of education and a number of cases with different years. Hist is a standard way of showing a histogram display of the output. That generates this graphical window here. We've got a histogram distribution for education years, and we've excluded or we've restricted it to those education years between 0 and 40. There are some higher values in the data, but we've excluded them from analysis. A bit more complicated code to do some things. A nice feature of R is the capacity to specify how many graphs you want stored simultaneously on the graph window. So this command here, par mfrow c22, says we're going to, from now on, the graphs are going to be stored in a 2x2 matrix. So if I do make that specification and then do one plot, what will happen is that plot will be stored in the first corner of a 4x4 matrix. This is actually the scatter plot between age and volunteering in its default format. Here's a second plot, which is going to be a bit more complicated. We do a scatter plot first, then we actually do a regression model and add on to the scatter plot an additional line summarizing the regression model. That goes in the second part of the matrix. So some nice facilities available in R for graphing data. But as I'm skimming over the code, you can hopefully see that it's a bit less trivial, a bit more complicated than in the case of Stata and SPSS. The other comment to make, or I won't illustrate in depth, but the other comment to make about using R for analysis and graphical presentations is that many of the more complicated things are available through what are known as extension libraries. So ggplot is an extension library for graphing in Stata. some of the analytical commands equally, some statistical models require extension libraries to be run. So when I run library ggplot, and then that means that there's a bunch of commands available from the extension library ggplot that now become available to me. qplot, for example, is a quick plot in a format that's the standardized format of ggplot. So if I run these lines, the default histogram has a certain appearance to it. But if I redo the histogram in the quick plot format, we have a different style and appearance and different layout as well. So there are lots of possibilities, but they become rather complicated rather quickly. So hopefully that quick illustration of using these packages in practice, along with the discussion of what we can potentially do with statistical data visualizations using software packages, is of some use to anybody thinking about doing an analysis of data and summarizing results in statistical data through graphical packages.
Okay, so my talk there on using software for producing statistical data visualizations, looking at some of the technical features of producing graphs based on statistical data. The next talk we're going to show is by Orian Brook, who again is a researcher on the Civil Society Data Partnership Project at the University of Stirling. Orian's talk is going to be about visualizing geographical variations, and it goes on for about 23 minutes.
Hi, this is Orian Brook, and in this section of today's webinar, I'm going to be talking a bit about visualizing geographic variations, i.e. maps. There are some particular problems with mapping data, which must be acknowledged. It's tempting to think of maps as being factual, but in fact they are certainly maps of data tend simplifications of a great deal of underlying detail, so that what it can be said that it's just as important what is sometimes left out or elided together as what is represented. As it says here, they're simplifying complex reality, and any map that you see should be considered to be only one of potentially many ways of presenting that data, many of which may be equally acceptable or correct, some of which might be downright misleading, but there are lots of possibilities in terms of presenting maps, some pitfalls to avoid, and some tips which I'm going to be discussing today. Those quotes are from a book, amusingly named How to Lie with Maps, that has a lot of advice and examples. Of course, maps can be intensely political too, so it has a lot about the history and politics of mapping, certainly recommended. There's also Danny Dorling, very famous a geographer looking at spatial inequalities, and his book from 2012, The Visualization of Spatial Social Structure, deals a lot with these themes, actually a reworking of his PhD thesis, I believe. So we're going to be talking about a few particular issues with mapping today. First of all, we're going to be talking about the variations in population density, which can be a particular problem, in fact, in mapping data in Scotland. We're going to be talking about the choice of data ranges and how that can affect how the map looks and the story that it tells. We're going to be talking about the differences in area aggregation, or the choice of areas that you map. And then we're going to be talking a little bit about the colours that you choose. As I said, with most maps there certainly isn't one right answer, but a few things to avoid. So first of all, population density. This is a map of the most recent urban rural indicator for Scotland. And as we can see, the remote rural areas, represented here in dark blue, dominate the map, but in fact they only represent 18% of the population of Scotland. In this case, as we're looking at a measure of virality, then that is quite correct. But for example, if you're looking at a political map, and if that were voting intention, then one might get a rather misleading impression of how Scotland votes. Based on if you were looking at constituencies of different colours, for example. It also means that it's very difficult to see the detail of where most of the population resides in the Central Belt, and of course the other cities such as Inverness and Aberdeen, and indeed 70% of the population live in the rural areas. So there is a particular option for dealing with this, or a range of options, called the cartogram, where the size of the area that's represented is adjusted or scaled according to various factors, most commonly the population of that area. So in theory, the advantage of this is that, for example, in the case of that rural urban map, it would display both the population size and the rurality of the area. But in practice, it has some disadvantages. So, for example, this is a map of the crime, one of the crime measures in the crime dimension of the Scottish indices of multiple deprivation. And we can see here on the left what one would see as a typical map of the number of crimes per 10,000 population within different data zones in Scotland. And on the right, we have a cartogram of the same map. And we can immediately see the disadvantages here in that the map is unrecognisable. One can tell, looking at, for example, you can see the Clyde Valley in the west, you can see the Firth of Forth in the east, so you can roughly tell where Glasgow and Edinburgh are, especially by comparing it to the map on the left. But it's very difficult to actually get a sense of the geography of Scotland from that map. The main disadvantage of cartograms is that they can make the maps very difficult to relate to geography as we know it. There are some options as to how much the map is rescaled, is reshaped, but then the issue is also then it can be slightly difficult to know really what you're looking at. Obviously, in the example that we can see here, which is taken from a site called worldmapper.org, which has many, many maps, this is one where the countries are rescaled according to extent of infant, in fact, female infant mortality in this case. Obviously, with such a recognisable map like this, it can be easier to share where the countries are and recognise the continents. So it's not like a cartogram is never a useful approach, but it certainly has its drawbacks. This is a different kind of cartogram. In this case, these are local election results, and each of those blocks represents a local council. Now, this is a much more recognisable shape of the UK in this case, comparing the results from 1974 and 2008. So one can more easily see where different parts of the country are, although it's still fair to say that it would be a little bit difficult to pinpoint precise geographic locations if you're looking for it. So they can be good for some overall geographic patterns, but can be difficult to actually look at the map in much detail. So what are the solutions to this? I think the most important one is to be careful about how you interpret a map and think about what portion of it you map. If you're mapping areas with very different population densities, for example, you can think about zooming in on areas of interest, or just think about when you look at the map, A, think about how you interpret what you're seeing, and B, think about how you communicate that to an audience or to a readership. Another very important issue to do with mapping is data ranges. There are options for, and this refers to how the data is summarized within the map, how you group the different areas that you're mapping. So there are three common approaches that one might be presented within mapping software, or most commonly used. There are quantiles, which refers to what a fixed proportion of areas falling into each group in the quantile. For example, there are further names depending on the number of groups. So quartiles for 4 groups, quintiles for 5 groups. Most familiar from the indices of deprivation, deciles for 10 groups, and so on. There are equal interval where you map, for example, where between 11 and 20% of the population do this, and then 21% to 30%, and 31% to 40%, and so on, or could equally refer to count data. Or there's simply manual ranges where you choose ranges of data that best fit the data and your interpretation of it. Bearing in mind that the best approach will depend on the data that you have and what you want to say about it, and ultimately your choice of data range. It's quite possible to do something potentially misleading with the data range, and so in terms of thinking about whether what you're doing is correct or truthful, you have to look at, well, do you feel that it appropriately represents the underlying data? And that might imply a little bit of fiddling around with it, trying different approaches. You will end up choosing one approach where you feel that it most easily visualizes the data that you have and what you're trying to say about it, but equally you wouldn't want somebody else to come along and do another map with exactly the same data telling the opposite story. And there's also the question of which actually provides the most visual discrimination and allows you to compare areas, for example, most easily. So looking at quantiles, the advantages of the quantiles is that they are easy to relate to, easy to communicate. So for example, you can immediately look at a map and say the most 25% most deprived areas. You always get a map with a good range of colours, which will come on to how you choose the colours, but you will always get a good a variety, a range of colours across the map. Which is helpful. You get a consistency of approach, which can be good for comparing different data, different kinds of counts. So, for example, if you're looking at quantiles, the lowest quantile might be the 25% areas with the highest crime rate and the 25% areas with the lowest income. You're not measuring crime or income on the same scale, but those 25%. That 25% is measured on the same scale, so it's a consistent approach. There are some disadvantages. It's not good for skewed data, and it's not good for data that exists in a very narrow ranges, or for data with big clusters in. So, for example, the examples I put there, the percentage Chinese, where in general, I'm picking these figures out of fantasy, but if we say that in general the percentage of people who identify as Chinese in a data zone would be very small, something like between 0% and 1.5%, but then there will be clusters, geographical clusters, where there are much higher percentages. So but that will be a very small number of places. So if you simply did quartiles, you would end up with the top quartile where something like between 1% and 25% of the population, say, identified as Chinese, which is a very wide range. And equally, where you have a male-female ratio, you have the opposite problem, where the male-female ratio doesn't vary very much. I mean, I guess a little bit more by data zones, but overall the male-female ratio is relatively constant across the country. So let's say you might have 4 different quartile ranges that might be 48% to 49% male, 49% to 50% male, 50% to 51% male, and 51% to 52% male. So you would represent those as being at 48% versus 52% as being at the opposite ends of the spectrum, but in fact they are relatively close to one another, relatively similar. A second approach is equal interval. The advantages of this, again, are that it's relatively easy to communicate. People can understand what you're showing them, between 10 and 19% of the population, for example. They're good for showing contrast of the same measure. So, for example, if you wanted to map, first of all, if you wanted to map different qualification levels, you could compare areas with 30% or more graduates versus areas with 30% more people with no qualifications. You would get very different areas of the map appearing, obviously, in most cases, but at the same time, it's a constant quantity. The disadvantage is that there's no consistency of approach when you're comparing different data. So, for example, if you're mapping crime rates, if if you wanted to map the number of burglaries in an area or the rate of burglaries in an area versus the rate of arson per population, per head of population, there's no way of choosing what numbers would make those ranges comparable. So you could end up choosing almost anything. It's also more dependent on the variability of the data, how, in technical terms, what the standard deviation is, and it also doesn't work very well when it's skewed. And we're going to come and look on a couple of examples of this. This is from a wonderful website, petitionmap.unboxed. Sorry, from Unboxed Consulting. And they map the people that sign all the petitions that go to the UK government, and which Westminster constituency they belong to. It's a wonderful website, fascinating reading. My only gripe with it is that it uses equal ranges for the mapping, and you can see an illustration of the disadvantages of this here in two different maps. On the left we have a map of the number of people. It should be a rate of people ideally, but sorry, this is my other gripe with it. It should be a rate, a proportion of the population, but it's not. It's a count of the people who signed a particular petition. On the left, it's the percentage of people who believe that we should stop spending 0.7% of our gross national product on foreign aid. I assume that they mean that we should spend less. Anyway, we can see most of the map is quite dark. It's quite dark red. And that's because although the range goes up to 561, most of the support for this is relatively well spread, so that the average is probably 480 or so, and most of the constituencies are grouped in the dark categories on this map. So it doesn't show you very good discrimination. You can't really see where are the areas of people where the support is higher. On the other hand, on the right, we have a map with the opposite problem, where there are just a very few clusters of areas with slightly higher support for this. And in fact, it also goes back to our first problem, because the areas with higher support for this petition, which was to Parliament to sit on Saturdays, this is relating to Jeremy Hunt's demand that consultants should work on Saturdays, that should be treated as a normal working day. The clusters of support are relatively limited, and they tend to be in quite small, presumably very urban areas, so that they're hard to see, and most of the map is pale yellow. So, illustration of the disadvantages of the equal interval approach. And here we've got a comparison of the quartiles versus the equal interval approach with the rate of with the crime rate in Scotland. So according to the indices of deprivation, on the left we have quartiles. We can see roughly where the areas of relatively higher and lower rates of crime are. On the right we have equal interval, and we can see it's very good at showing us where the biggest clusters of crime are, but it's not very good at showing us much differentiation elsewhere. There is something else to point out with the disadvantage of the quartiles. Well, it's something I discussed before. You can see the top range, that actually the crime rate for the top group is very, very wide. 539 crimes per 10,000 to 15,916. So in fact, ideally, the best thing to do with that map might be to look at a larger number of categories, quintile or decile, say, or to look at a different approach, to look at a manual map, and you can just choose categories that make sense. So more than 1,000, more than 10,000. Crimes per 10,000, for example. There is also an approach which professional mapping software will offer you, which is the natural breaks, which is a statistical approach where the software chooses the breaks for you. The third issue I'm going to talk about is what's called aerial units, i.e. the different areas that you're choosing to map. And the issue is that depending on what type of area you map, you will get different results. You will get a different map. Technically in geography, this is known as the modifiable areal unit problem, because as data, let's say data on individuals, is aggregated to different and especially larger geographic units, the proportions of belonging to different population groups will change because the variances in the data are smoothed out. So you might have some areas with a very high or very low proportion of a particular subgroup, say people with people with a degree, or people with a PhD, for example, might be clustered around a closer university, depending on the university. So you will see very wide variances in the number of people with a PhD in an area when you look at small areas. But the larger the area you look at, the more those wide differences will be smoothed out. As a result, an example of this is that this happens more in England, I believe, but you get different parts of England, Liverpool, Manchester, East London and so on, laying claim to being the most deprived area, depending on what level of geography you're looking at. So the most deprived data zone, which I believe is actually currently in Essex, the most deprived ward, the most deprived local authority, which I think normally it might be, depending on what measure you're using, it might be Tower Hamlets, it might be Manchester, it might be Liverpool, the most deprived parliamentary constituency, and so on. You will get different claims to deprivation based on different areal units. Here's an example of how this might happen. This is a very famous map in social sciences. A man called John Smoe produced this map of cholera deaths when people didn't know how cholera was transmitted, basically. Here's this map of some deaths in streets in London. The black circles on the map are water pumps, and the black dots on the map are people dying of cholera, and he was able to show clusters of deaths around the Broad Street pump in the centre, and showed that in fact the water that being extracted from that pump was infected with cholera, and that's in fact how they discovered how cholera was transmitted. But you can see on the left, and this, I'm sorry I didn't credit it, is from the Marc Monmonier's book, The How to Lie with Maps, how if you took different aggregations of that data, measured it in slightly different area units, you could get some very different results. Only the top aggregation would actually give you a reasonably correct inference from that data, from that point mapping. The other two are not giving you very useful information, and in fact the bottom one is somewhat misleading. Finally, I'm going to talk a little bit about colours. So there is a temptation when you start mapping to think that the greater the contrast, the better. So, for example, to use hot-cold maps is very often done. Let's say going from blue to the areas with the lowest numbers, to red to the areas with the highest numbers, and different colours in between. There are disadvantages to doing this. First of all, they won't print in black and white, and they won't photocopy. Secondly, they can look different on screen, or different screens, or different projectors. In fact, I've had this experience of presenting a whole load of slides of different charts where the colours that I had designed on my computer didn't look at all the same on the projector, and in fact two of them were indistinguishable. Also consider colour blindness, which affects 8% of men, fewer than that of women, but red-green colour blindness being the most common, I believe. You may find that a range of similar colours, like different densities and different depth of colour, can actually work better for presenting data. Here's an example, again based on the indices of deprivation and crime data, where on the left we have the different densities of colour, showing, you can see where the areas with the highest crime rates are in the dark blue. On the right, we have a hot-cold map where the areas with the highest crime rates are picked out in dark red, and next is pink, and so on. Now, you can see that visually those areas in dark red do pop out, but it perhaps suggests a qualitatively different relationship to the other area, which isn't particularly the case. So you can see that that choice of red would actually help if you really wanted to highlight those areas, but it may be misleading in terms of the data that you're presenting. If you want to have a go at making maps yourself, you can have a go at making maps like this, choropleth maps. You can try a website called indiemapper.com, which is free, and has also some very useful guidance about how to make maps, where to get the data from, how to choose colours and so on. That's it. Thank you for your time.
Okay, so a presentation there from Orian Brook on aspects of visualization with geographical data. This is a theme that's come up quite a lot in our webinar series. We are aware that a lot of the times when people have got data or are interested in civil society in Scotland and patterns, are often interested in geographical variations. So I think Orian's presentation is a really useful, thorough review of the challenges and issues associated with geographical visualizations. So we'll move on now to the last of the presentations in today's webinar. It's by Alasdair Rutherford again on the theme of visualizing uncertainty, and this is about how we deal with statistical data, most statistical data actually, which has some information about uncertainty of results. How do we effectively communicate that through visualization or other means? So Alice's talk goes for about 18 minutes long.
One of the big challenges in communicating the results of a data analysis is explaining the uncertainty around the findings. Often it's tempting to focus on the value of statistics that have been calculated and presented, and it can be easy to ignore that these have come from a sample, that there's some random noise, and that therefore there's some uncertainty around estimates which needs to be communicated. In this talk, we're going to look at some ways of visualizing uncertainty using graphs, charts, and information visualizations in order to get across the level of uncertainty in an analysis. So first of all, we need to think about what we mean by uncertainty. If we calculate an average in a data set, we get one number. That is the average from that set of data. But usually our data will be drawn from a sample of a population. We could have had a different sample from the same population, in which case we'd have got a slightly different average. So there's some error in the measurement of that average. That means that we don't really have a precise estimate of the average in a population. Rather, we have some uncertainty about its true value. And we want to be able to communicate that level of uncertainty and how confident we are in the estimate that we have. So when we're doing some data analysis, we need to think about ways to communicate that uncertainty. One of the simplest ways to show uncertainty is just to show the distribution of a variable. So here's a histogram of age, and we can see the wide range of ages of people in the sample. And we can also see the relative frequencies of people with different ages. So we have some sense of the distribution and how many people there are of each age. Of course, showing all the data like this doesn't really summarize. It presents a lot of information, but maybe what we want to get across is some measure of the typical age, and that might be why we're wanting to use an average. So perhaps there's too much information shown by graphing all of the data. A box plot, which we saw earlier, conveys more than just the average without showing the distribution of all the data. So it gives some sense of the spread, as well as some measures of the middle, the mean and the median, and gives us an indication of whether there are outliers. So from the box plot, we can see whether all our data is concentrated around a particular value, or whether there's quite a big spread of values, and whether there are a number of values that are quite far away from the middle. And that might tell us something about our uncertainty about typical values. So it's important when using descriptive statistics that we use measures of spread as well as measures of the middle. By measures of the middle, I mean the different sort of averages that you might use for different types of data. So the mean, which is what people often mean when they talk about averages, the median, which is the central value, and the mode, which is the most common value. For a set of data, these are going to give you one number as a measure of that middle. But we also want to communicate how spread out that data is. So we should really also report measures of spread. The simplest measure of spread is the range, just the highest value minus the lowest value. And that gives us the total extent of all the possible values in our data. Slightly more sophisticated is the interquartile range. And that gives us a distance between the data point that is 25% of the way through our data and the data point that is 75% of the way through our data. So we've got the size of the middle 50% of our data points, the range that half our data lies within. And the bigger that is, the more spread out our data is. But then the most useful measure of spread is the standard deviation. And that's giving us a kind of average distance from the average for our data. And so a bigger standard deviation means that our data is more spread out. So it's important to use both measures of the middle and measures of spread when describing a data set. But if we then calculate these sorts of estimates, both measures of the middle and measures of spread, because we've drawn a sample, and we could have had a different sample if we'd drawn it at a different time and got a slightly different combination of people, that means that there's some error in our estimation of those sample statistics. So we want to be able to communicate. So we want to be able to communicate some measure of that error. And the most common way is by reporting the standard error, or to use the standard error in order to show a confidence interval, a range in which the likely values for our sample statistic lie. And that means that instead of just reporting a point estimate, just one number for an average, instead we're able to give a range of probable values for that estimate. The bigger the range is, the less certain we are about the value of that characteristic. Whereas the smaller that range, then the more confident we can be that the sample statistic has a particular value. So confidence intervals can be really useful in communicating the level of uncertainty in the analysis that we are presenting. One of the challenges in communicating uncertainty is that probabilities aren't very intuitive and they can be quite difficult to understand. So we've got a reasonable idea that a 5% probability means that something's going to happen about 1 time in 20. But we don't necessarily have a good feeling or a good intuition for reasoning with those probabilities. And so it can be difficult to communicate probabilistic information. One common way to try to communicate probabilities in an accessible manner is to instead use frequencies. So if we're wanting to communicate probabilities associated with some sort of test, perhaps a medical screening test, then we need to communicate the probability of an individual having an underlying condition. But then we also need to communicate the probabilities that the test is going to make a mistake, that is going to indicate that somebody has a condition when they don't, or indicate that they don't have a condition when they do. And that means communicating conditional probabilities. What's the probability of having a condition given that the test has given you a positive result? And conditional probabilities can be quite unintuitive, but presenting these as frequencies can make it much more accessible. And you can see this visualized in the graph here for a cancer screening test, which shows that even with a positive result on the test, the number of people that will actually have the underlying condition is quite low, and therefore the probability is still quite low. But that's easier to communicate by showing the frequencies than it is by communicating the raw probabilities. And this is because people find it quite difficult to think about conditional probabilities and then to compare them with each other, whereas we find it much easier to work with frequencies, and particularly when they're presented visually. Often when we're doing some sort of data analysis, we're going to be making predictions. In a sense, when we calculate an average in a sample, we're making a prediction about what the average in the population is. We can't measure everybody, we're only able to measure a sample, but the results of analyzing that sample tell us something about the population, or at least let us predict something about the population. But in other cases, we might be using our analysis to make predictions about the future, for example. And we want to be able to communicate the uncertainty associated with those predictions. Here's an example trying to communicate the different likely temperature changes as a result of climate change in two different scenarios. On the left is no climate change policy, and on the right is the enacting of a climate change policy that should have a significant effect on climate change. And what this graph shows is a comparison of the two scenarios with the probabilities of different sizes of temperature change shown as slices in the pie charts. So the areas of those slices show the probability of different outcomes. So we can compare the two scenarios, and we can see that the likely warming effect on the left with no policy is larger than the warming effects on the right-hand graph with the policy. But it also shows that within each of the scenarios, there's quite a lot of uncertainty about exactly how big the temperature change might be. So there's a reasonable range with the policy from 1 degree rise to a 4 degree rise, but with a much higher probability for a rise of between 2 and 2.5 degrees. Without the policy, the most likely rises are between 4 and 6 degrees, but there is some small probability of either smaller or larger rises in temperature. So rather than just reporting individual figures underneath the two scenarios, we're able to get some sense of the distribution of possible outcomes and the uncertainty associated with those. Sticking with a weather theme, here are some predictions for the range of maximum temperatures on different days. And this graph shows for each day both the predicted temperature in the yellow box, but also the range of likely temperatures around that prediction. So these are all estimates of what the maximum temperature might be on a given day, but we can see that on some days there's a lot more confidence in the prediction than there is on other days. So there's a much smaller range on the Tuesday than there is on the Wednesday. So we have more information about how well we can trust that prediction rather than just reporting the 8 degrees and the 10 degrees for the two different days. We're actually able to see the uncertainty associated with that estimate. We mentioned confidence intervals around estimates as giving a likely range for the possible values of an analysis. So one way to communicate them is to put those ranges into a table or to illustrate them with a horizontal line and a point estimate. So this table here shows risk ratios, and the horizontal lines show the confidence interval around the estimate. So we can see for different studies, there are different levels of confidence in the estimate, but we can also use the confidence interval to judge whether this is good evidence of there being an effect. We can use visualization to communicate more complicated predictions as well. This visualization shows the prediction of the path of a hurricane in 2005. So the analysis of the data gives a most likely path shown by the black line, but there's quite a lot of uncertainty associated with that estimate as well. And so the white area around that estimate shows the other possible paths that are also reasonably likely within the predictions from the model. So rather than just focusing on the most likely prediction, we're able to get a range and some sense of the uncertainty around that prediction plotted onto a map. In many cases, our predictions will be of the form of trying to predict the trajectory of a particular variable off into the future. So we might be wanting to look at projections of the volunteering rate or the number of employees in the third sector, for example, or of income for particular organizations. In the visualization here, this is estimates of growth provided by the Bank of England. So the black line shows the observed data for growth. And then this graph makes predictions beyond 2007. And you can see the predictions are represented as a fan chart. So we can see these contours of green showing the range of the predictions, with the darker green central contours being the most likely values, and with the uncertainty fanning out as we get further into the future. So the further we are away from the data we observe, the less confident we are in our predictions. So this gives you a good sense of the uncertainty associated with the predictions and how that changes over time. From its wide range, you can also see why just relying on a point estimate on one value might be quite dangerous. And in fact, the Bank of England in general refuses to provide point estimates for these sorts of far-off predictions for just that reason, that people will then focus on those individual numbers, when it's far better to think about the predictions as being a range and with an uncertainty across that range. So let's think about some general lessons for visualizing uncertainty. First of all, probabilities are not intuitive, and people find it difficult to reason and think about probabilities. So we need to be quite careful when communicating them, and to think about different ways in which we can get that information across. And that could be through presenting frequencies, through presenting ranges, and thinking about the style of that presentation. You'll probably want to use multiple formats. Different presentation styles are going to suit different audiences, and some people are going to prefer to see the range of numbers, and some people are going to prefer to see a visualization of that range, and some people might find the presentation in frequencies to be more intuitive. And because of this challenge in thinking about probabilities and risks, it's important that you communicate both absolute and relative probabilities. This is the situation you often see in newspaper reports of probabilities, where something is shown to decrease your risk of heart attack by 10%. But that's a relative risk, because it's 10% of your underlying risk, which might be quite small. And so the actual difference in your absolute risk might not be very big at all. In order for people to understand that, it's important that you report both absolute and relative risks. The more general data visualization principles apply when visualizing uncertainties. So the best graphics are going to be well presented with clear explanations, good choice of color, well labeled, and well explained. It can be really powerful to use narratives, images, metaphors in illustrating your visualization, and that can really help people to understand them. But remember that you should be presenting the facts. You should be letting the data speak. So you have to be careful about using particularly emotive imagery that might detract from actually understanding the underlying data. And in making these sorts of decisions about your visualization, anything that you produce is going to have limitations. It's only going to show part of the story. You have to make some decision about what to show and what not to show. So you should make it clear what it is that you are showing, what the story that you are telling is, and also what has been left out. So our takeaway messages is that it is really important to communicate uncertainty. And this is true whether you're just reporting simple averages or whether you're reporting the estimates from complicated statistical modeling. If you're reporting statistics drawn from a sample, then they are measured with some error, and you should give some indication of the size of that error, the size of that uncertainty. Visualization can be a good way to communicate these uncertainties, and it can be more intuitive to help people understand what can be a difficult concept. And there's a wide range of techniques and different visualizations, particularly for communicating uncertainty, which you can use when you're trying to get these messages across.
Great. So a presentation there from Alasdair on the theme of uncertainty and how we summarize and visualize uncertainty in data. As ever with all the presentations we've been shown today, there are materials you can access online via thinkdata.org.uk. Please do go along, and you can download PowerPoints and appendix materials when relevant. And we hope for those of you who've been watching today's session, again, you're seeing examples of how the debates about methodology and data analysis that are often in universities are relevant to wider areas of research and use of data resources in today's theme in the context of visualization, in other webinars, in other thematic areas and topics. Okay, so we'll wrap up there at the end of the 6th webinar on approaches to visualization.